So you have already done stoichiometry, you just didn't know it. Did we talk about the fact that we were doing stoichiometry when we were doing stoichiometry? Good, because I didn't used to explicitly talk about the fact that you were actually doing it. What you have done previous to this is composition stoichiometry, which is just looking at how many moles of carbon are in 100 grams of carbon, how many, blah, 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 how many moles of water are in 100 grams of water, that kind of thing. It's mass relationships. It's all about going through, math to mole to gram conversions, gram to molecule conversions, knowing how many pieces there are. In reaction stoichiometry, what's cool is we can start to look at how many grams of this will react how many grams of that. If we put together this many grams of this and this many grams of that, how many grams of this other thing will we produce? So to do that, of course, you have to be able to write formulas, correct formulas. You have to be able to write equations and balance them. And you have to be able to predict products. And once you can do all that, then you can start figuring out how much stuff you're going to produce. Or if you need to produce this amount of stuff, what mass of your reactants are you going to need? So that's where this goes. There are 4 basic problem types. And I'll tell you what the most... So you can have a given and an unknown in moles. You can have a given in moles and an unknown in mass. You can have a given in mass and an unknown in moles. Or you can have everything in mass. Guess which one we use most commonly? Everything in mass. Because there is no such thing as a moles scale. If you're measuring out a quantity of a reactant, you're not measuring it in moles. You're measuring mass in grams, and you have to know how many moles that is. So you have to do the math on the back end. So we will practice all of these kind of problems, but I'm going to tell you that by the time you get to the test, the only ones you're really going to be doing are mass to mass, which makes it really tricky when we throw one in that's, mass to moles and everybody goes beyond. So, because mass to mass is the only one that really gets used in the real world. Okay, so the whole central heart of stoichiometry is the mole ratio. And it's just a ratio of how many moles of this produce how many moles of that, and then we take that out and figure out how many grams. So these are all factor label problems, and these are like 4-step factor label problems. They're beautiful, they're elegant, and if you do it right, they pretty much solve themselves, which is nice. Okay, so we're given an equation here. Anybody want to read this? If we want to read all the information that's in there, we could say 3 moles of potassium hydroxide will react with, and you're right, that is hydrogen phosphate. That is also known as phosphoric acid. Pretty nasty stuff, though you've probably pop. It's a common ingredient in pop. So 3 moles potassium hydroxide plus phosphoric acid. We can look at the ratio of potassium hydroxide to phosphoric acid. It takes 3 moles of potassium hydroxide to react every 1 mole of phosphoric acid. We can look at the ratio of potassium hydroxide to potassium phosphate. For every 3 moles of potassium hydroxide you put in, you're going to get 1 mole of potassium phosphate out. That doesn't sound like a very good deal. We can look at the mole ratio of phosphoric acid to water. For every blank moles of phosphoric acid, go ahead, fill it in. 1 mole. For every 1 mole of phosphoric acid you put into this reaction, how many moles of water are you going to get out? 3. Now, you can also look at all of these sort of in reverse. Okay, so we can also look at this kind of what we think of as backwards and say, well, for every 3 moles of water that we want to produce, we're going to have to put in 3 moles of potassium hydroxide. For every 1 mole of potassium phosphate we want to produce, we're going to need 3 moles of potassium hydroxide. So every single one of these ratios goes in both directions. Does that make sense? So out of this, and this is a whole factorial thing, let's see, 1, 2, 3, 4, 5, got that one. So that's 5, so that would be 10, right? How many do I have listed? 1, 2, 3, 4. I only have 4 listed, so I missed 2 of them. It's easy to do. Okay, so now that you know what a mole ratio is, let's play with them. Okay, so with that ratio, what you can do is figure out how much of something you can produce. Pretty easy. We're going to just stick with that formula because we've got it already. So if you were given 9 moles of potassium hydroxide, how many moles of potassium phosphate could you make? Well, 9 times 1 divided by 3, you'd get 3 moles out. Now we would set that up as a factor label. And this is the point where I've been saying all along, put your units, put your chemical. Put your units, put your chemical. And you've been thinking, oh, well, that's ridiculous, Moser. It's all the same chemical. It's not anymore. This is the point where you're going to have multiple chemicals in the same factor label. So you have to be absolutely certain that you know which chemical you're talking about. So let's practice one of these. Let's say I give to you 4.7 moles of potassium hydroxide. How many moles of phosphoric acid do you need to react that? So, and we want to know, here I'm going to put this here, given that, how many moles of phosphoric acid, H3PO4, do we need? Well, we just look at the mole ratio. So, when we start any factor label, what do we start with? Always, always, always. First box, given. And we're going to put in our given with units and chemicals. So 4.7 moles potassium hydroxide. What units and chemical need to go in the next box down on the bottom? Units and chemical to cancel. Moles. So we need the units and the chemical in these 2 boxes to be identical so that they cancel out. So we're going to put in moles of potassium hydroxide. Now, what do we want our answer to be in? Moles of phosphoric acid. H3PO4. Okay. So what units and what chemical have to go in that top final box? Moles of phosphoric acid, H3PO4. Now, where do we get our number values to put in there? It's our mole ratio! So, whatever number is your coefficient in front of potassium hydroxide is what's going to go down there. And whatever number is in front of your potassium phosphate, which I put the 1 in, I don't usually do that, I don't know why I did that, is what's going to go there. So we know that for every 3 moles of potassium hydroxide that we react, we're going to need 1 mole of phosphoric acid to run the reaction. Okay, now we just do math. Okay, we get 1.56 repeating out to infinity moles of phosphoric acid are required. Now, how many sig figs do we have? 2. So that's going to be 1.6 moles of potassium hydroxide. Okay. So, given this question, we're using the same reaction, potassium hydroxide and phosphoric acid. It's a neutralization reaction. We're producing a salt, basically, and water. Given 3.75 moles of phosphoric acid, what mass of potassium phosphate can be produced? So, as always, what goes in the first box? Given! And our given is? So we'll take it from the Pacific Northwest. Yep, 3.75 moles of H3PO4, phosphoric acid. Now, it's always helpful to think about where we want to end up. Where do we want to end up? Grams of potassium phosphate. So, that just gives us a roadmap when we get towards the end. What units and what chemical have to go in this next box down on the bottom? So we'll take it in the Old South. Units and chemical. Bottom of the next square. It has to cancel. Moles of, yeah, H3PO4, hydrogen phosphate or phosphoric acid. Okay, now here's the tricky part. The top of that box, we're trying to get to grams of potassium phosphate. Can we go straight from moles of one thing to grams of another? No. We have to go through the mole ratio. So we have to know how many moles of this produce how many moles of that, and then on the end, we can convert back into grams. So, units that are going to go on top, moles of K3PO4. And I'm not even going to worry about filling in numbers yet. So what units, what chemical go on the bottom of the next box? Somebody from this desert Southwest. And that'd be just two of you today. Jeremy, that's you. You're the desert Southwest. Yeah, because we have to have those units and chemicals so they'll cancel. So, moles of potassium phosphate. Now, we want to end up in grams of potassium phosphate. Is there a relationship between grams of potassium phosphate and moles of potassium phosphate? Hey, Texas. Is there some relationship we know of between grams and moles? Yeah, so we need to end up in grams of K3PO4, and the relationship between moles and grams is going to be the molar mass of the compound. So I guess first of all we should fill in the mole ratio. So what number is going to go here? Hold up fingers, vote with fingers. These are all small whole numbers. What number is going to go right there? Fingers, 1, yes. Because we're looking at the coefficient in front of H3PO4 and there's nothing, so it's a 1. What number is going to go in front of K3PO4? 1. It's a 1-to-1 mole ratio. These are nice. They're very easy. Okay. Now, here is part of what I've heard called the 10 commandments of doing reaction stoichiometry. Thou shalt not put any number other than 1 in front of the word moles unless it is a given. So, let me ask you, on the heels of that, what number is going to go here? 1! Don't even make some kind of smart aleck remark, Texas. I saw you formulating something. It's always the northern panhandle. Okay, now, we're going to get that number for grams of K3PO4 from adding up the molar mass of K3PO4. So we got to do a little bit of work here. Okay, so for the molar mass, I'm getting 212.27 grams of potassium phosphate in a single mole of the stuff. And that's, of course, doing my standard trick of going to two figures. Okay, so now how many grams of potassium phosphate are we going to make, starting off with 3.75 moles of phosphoric acid? So as a brush-up refresher on factor label, you multiply everything that's side by side, and you end up with one big number on the top. Then you multiply everything down here that's side by side, and then you divide the top by the bottom. So multiply across the top, multiply across the bottom, divide everything. What do you get? 7. Do you have a calculator, sir? So we get a raw answer of 796.0125. How many sig figs do we have? fingers. 3. Because we look at this, and that's what we're working with. That is 3 sig figs. So our final answer would be 796 grams. Potassium phosphate. All you're doing, if you look closely at this, what I want you to realize is that this is the problem you did last time. That's a mole to mole. All you did was add a step on the end, which is the conversion from moles to grams. Now, let's do a grams to moles. Okay, so I changed the problem up a little bit. Same reaction, and I'm actually using the same things. I'm using the phosphoric acid and the potassium phosphate. So given 100 grams of phosphoric acid, how many moles of potassium phosphate can we produce? What goes in the first box every single time? All together now. The given! It's like, hey, Norm, you don't know what that means. And, you know, it's always nice to keep our eye on the ball. What units and chemical do we want to end up with? Old South, you got something for us? What units and what chemical do we want to end up in? Okay, so we're starting out in grams of phosphoric acid. What units and what chemical go in the box? In the box, down, and next. Grams, I hear grams. H3PO4. Excellent. Gesundheit. So, what is going to have to go above that? In the center of these problems, we always have to get to moles. Moles of, because there's always a relationship between moles and grams. Moles of H3PO4. So what's going to go in the next box below? Units and chemical have to cancel. What is it? The Great Mossy Northwest. What say you? I think I heard the right thing. Okay, same thing, yeah. Moles of H3PO4. We want to end up in moles of K3PO4. Is there a relationship between the moles of H3PO4 and the moles of K3PO4? Of course there is. It comes from the mole ratio. So we're going to go moles K3PO4. And now let's start plugging in numbers. So, thou shalt not put any number in front of moles in a mole to gram conversion unless it's a, thou shalt not put any number with moles except a 1 unless it's a ratio or a given. Okay, maybe that doesn't work so well. Maybe I need to recheck that. So, here, it's 1 mole of hydrogen phosphate, phosphoric acid. Where are we going to get the value for grams? The molar mass! So let's do that. The periodic... Okay, so I've got 98 grams of phosphoric acid in every mole of it. Where do we get our numbers for this mole ratio? From the coefficients in the equation, right. And in this case, as we discovered in the last one, they're both 1, which is nice. It's a 1-to-1. So how many moles of potassium phosphate are we going to make? Well, multiply everything across the top, you get 100, multiply everything across the bottom, you get 98. We're going to make, let me move this out so I've got a little bit of room, 1.020408, blah, 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 oops, moles of potassium phosphate. How many sig figs do we have? 4. 1, 2, 3, 4, all significant. So we're going out to here, and that 4 does not round up. So what we end up with for our final sig figs answer, 1.020 moles of potassium phosphate. So again, please notice, this is the problem that you did in the last one. Just a mole ratio. In the center of every problem, there is a mole ratio. There's always a mole ratio in the middle. What we did here is we just added on this step of converting it from grams into moles so that we could deal with the mole ratio. Okay, so practice 10 and 12 will get you some practice with the skills that we've just done. That's it.